All right, we are still in the preparatory chapter. We are moving on to P2 finally. If this didn't work. There it is, okay. And we're going to learn a whole bunch of integer exponent rules or exponent rules, and we're going to simplify exponential expressions, and then of course the application to his cool, awesome scientific notation stuff. So, all exponent rules. Maybe a good thing for you to look at if you want to, just sort of as a reference right away, is on page 25. And you guys have it if you have a little packet with you as well. It's on page where P2 starts. So on page 25, if you want to look for it, in that little box there right before the start of the homework, there's 1, 2, 3, 4, 5. 5 rules for exponents, and then the definition of exponents, and then the definition of a negative exponent. So you sort of have that with you. That'd be a good reference guide as we get started here. Okay, so very, very quickly, I'm going to give you the rule for it, and then we'll just jump into a few practice problems. We'll keep on going. Go. So it'll be sort of quick here. So let's go for it here. By definition, you guys already know this. A to the n means you're multiplying a n times. We call these guys factors. Right, so there's the definition of it. Let's jump to a practice problem here. And if you can do this in your mind, that's fine too. Cool. So just by the whole concept of definition here, this really means 2 times 2 times 2. Every good with 8? By definition, this actually means 3a times 3a times 3a. So 3 times 3 times 3 is 27. Okay. Let's start over. I'm going ahead of myself here, thinking where I need to be. Okay. How about 3a times 3a? We good? Okay. So 3a to the second means 3a times 3a, which really, in a sense, you're squaring the 3 and then squaring the a. Okay, then the fun one here is 1/2 times 4. This is 1/2 times a half times a half times a half. And the little rule that we've learned is you can just take 1 times 1 times 1 times 1, and then 2 times 2 times 2 times 2 makes the 16. Let me go back just a little bit here, show you a little something here students usually get confused on. So let's jump to this. Don't need to write it down unless you really want to here. But a is straightforward. 5 to the third power just means 5 times 5 times 5. Okay, negative 3 in parentheses to the second power. What that really means is, it means you're multiplying negative 3 times itself twice. We good? So negative 3 times negative 3, notice it turns into a positive 9. On the other hand, if you drop the parentheses, the difference between b and c, that's what I want you guys to notice. If there are no parentheses, this exponent of 2 is only acting on the number in front, which is just the 3. The negative just sort of hanging out in front. So in this case, this is what it means. It's a negative 3, or a negative times 3, which makes the negative 9. We good? Careful with parentheses. Without parentheses makes a humongous difference there. Okay, jumping to another definition. The whole concept of any number to the 0 power is 1. I wish they added a little extra piece over here. They should say, since you guys are sophisticated Math 15 students, they should actually say this, as long as a is not 0. Because you can't really have 0 to the 0 power. It doesn't make sense. Alright, same thing applies here. A cannot be equal to 0 or else this does not work. So a to the negative n, the negative exponent just means you change from numerator to denominator. If the negative is inside the denominator as the exponent, then you move it to the numerator, right? It's the switching of numerator and denominator. Okay, with that said, let's jump to this. It's all yours here. These are practice problems, so if you want to sort of see them.
But they're not in the printout?
They're not in the printouts, no.
Okay.
You actually have the answers to them on the...
I was looking for them on here and I was like, I don't see it.
No, no.
Okay.
The problems, the answers to them are actually in the book. It's the answers to practice problems right before the homework section starts. So, give you guys a whole 22 seconds. All right, 2 to the negative 1. Everybody good with 1/2 now? The 2 goes down to the denominator. 4/5 taken to the 0 power is 1. Again, any number taken to the 0 power is 1 except for 0. And if you have a fraction, all that happens, the 2 goes up to the numerator, 3 goes down to the denominator. But don't forget you're still squaring this. So 2/3 times 2/3 gives you 4/9 still at the end there. Okay, got a couple of people still writing it down. Go for it. Okay, so now let's review all the exponent rules or exponent properties. First one is this something called the product rule. And I think you know this already here. A to the m times a to the n. If you're multiplying numbers with the same base, all you got to do is add the exponents. All right, so let me jump to the slide here that has it. All yours for this one. Practice problem number 3. And again, we're just reviewing, so I give you a rule, give you a quick practice problems. We keep on going just to refresh your mind here. All right, these practice problems are very, very similar to the problems, the example problems. So if it's a practice problem number 3, if you still don't quite sort of like, I just don't get it, you can go back to example problem number 3 in the textbook. The problem would be slightly different, but the process would be virtually the same. So if you want to sort of take a second look of it. All right, so looking at this here, I see exponent of 3, oh, coefficient of 3. That goes down, but x squared times x to the 7th, I'm going to add the exponents to give me a 9. Cool. Going over here, multiplying all this together, so 2 squared. Don't forget the little square on the 2 here. Ooh, because of that, that means this could be actually a 4x cubed. Now we're multiplying a 4 to the x to the negative 3. That's cool though. Let's see what happens here. 4 times 4 is 16. X to the 3rd times x to the negative 3rd. It's 0, huh? And what's any number to the 0? 1. So technically, isn't this just 16 all by itself? 16 times 1 is just 16. Okay, so that was the product rule for exponents. Jumping to the quotient rule for exponents. Remember this one from algebra. If you have a number, 2 numbers with the same base, and if you are dividing those 2 numbers, all you really can do is just subtract the exponents. Are we good there? So it's a m minus n to give us the answer. Again, quick little example right here as well. And let's jump to a practice problem here. They're kind of getting a little more sneaky, so kind of careful there. But again, give you guys a whole 22 seconds. Cool. All right. So over here, for a to the 3 to the 4th divided by 3 to the 0. Technically, what we're going to do is we're going to put a base of 3, and it's 4 minus 0, which really just stays as 3 to the 4th, right? Because technically, isn't 3 to the 0 power just a 1? And if that's the case, then you have a whole piece that you have already. Okay, the next sort of slightly tricky one here is 5. Technically, this is 5 to the 1 power, is that right? So it's really... Oh, for A, sometimes the book wants to keep it in exponential form. Sometimes the book actually simplifies it some more. Either or, as long as you know you got the right answer, you're good. Okay, this one, 5 is going to be 5 to the 1 minus a negative 2, and that changes to addition, so how about 5 to the 3rd? And yeah, might as well simplify it here. 5 times 5 times 5? 125 is good. Okay, and this one, now you got a fraction, because 3 doesn't go into 2, so we're going to leave the 2/3 sort of out of this whole entire thing here. So how about 2/3 in front? And now we're going to do x to the 3 subtract a negative 4, which makes really x to the 7th. At this point, that is the most simplified version there. Okay, good there so far. Exponent rules coming back to your mind, is that right? Like, oh, yep, I'm getting these. I forgot, but I'm getting these now. To some. Okay, next. This is called the power of a power rule. What happens if you have an exponent inside a parenthesis, exponent outside a parenthesis? And again, there's like a little explanation there. But we find out by an example problem from pre-algebra, we find out, hey, you know what? All we really got to do is multiply the m and the n. Alright, so let's go for it here. Just some quick examples here just to make sure we got it. So simplify, write this without any negative exponents. Okay, so hopefully you saw this here. Exponent inside the parenthesis, exponent outside. Really, this is going to be negative 5 times 0, or just 0. And that eventually will still turn into a 1. Is that right? 7 to the 0 power is a 1. All right, the other way around. Still going to do the same thing. 0 times negative 5 is still 0, so you get the same exact answer both ways, both times. Okay, that would be still technically qualify as a pre-algebra problem because there's no variables of x or y or z or anything. So jumping to some algebra problems, let you guys try those. All right, so remember, in order for exponents to be simplified, we write them without having any negative exponents. So if you see a negative exponent, you still haven't finished the problem yet. Works about 99% of the time in calculus. 99% of the time, we would like to see positive exponents. There's sometimes, very rarely, very, very, very rarely, we actually want to keep the negative exponent because this problem looks a lot simpler that way. Again, very early in calculus. So most of the time we want to see positive exponents here. So in this case, how about x to the negative 8? Still not done. Where does the x go? To the bottom, or denominator. So 1 over x to the 8 would be the final answer. All right, going this way here, negative 2 times negative 5 would make actually already a positive 10, so no need to go any further. We are done once we take that step. Okay, here, so let's go with show of hands. How many say Mr. H? So far, P.2 is like the cinchiest thing I've ever seen. I could do it with only one eye open. Cool, okay. About 60% of the class. Okay, that's pretty good. Okay, All right, let's keep on going. Finish this off then. Something called the power of product rule. What happens if you have two things or a product inside the parenthesis? And you're taking a power of it. What happens is that power has to go to each and every single one of those terms. So the A has to have a power of n, and then the B has to have a power of n as well. And again, a little example here, if you need to. You need to have it here, but notice the 5 has to go to the base of 2. X15 has to also go to the base of 3 in order to simplify that problem. All right, so let's try it. And of course, I'm going to throw in negative exponents into the whole thing too. All right, 22 seconds, try it yourself. For some reason, I like the number 22. All right, so let's go with number 1. That little negative right here, hey, doesn't that little negative one just means reciprocal and that's it? So in this case, we're going to take the reciprocal of 1/2 x, so that means the 2 gets to go to the top. The x is a multiplier, so therefore it's going to go to the bottom, so how about 2 over x? Ah, now I see erasers happen here, okay. And someone being shy with their eraser, like doo-doo-doo-doo. Okay, let's go to this one here. So we got a 5x to the negative 1. It's taken to the second power, so that 2 has to go to the 5. Or we can simplify this already. How about take the x down to the bottom? Good there? And now we are going to square the 5, square the x, and we got 25 over x squared. All right, another way to do it, just to show you that really you don't need to follow, there's no order to exponent rules. So if I did it the other way, if I just did this right here, 2, 5 squared, then I went over here and I did x to the negative 1 squared, that would give me a 25 here, x to the negative 2, and eventually I would still have to take that x down to the bottom, and there it is, I still have the same answer. Good. So for exponent rules, there's technically no order to them. You could reverse them, you could do it any which way as long as you're just simplifying the problem. Okay, so with C, that's a straightforward one here. X3 goes to the x, and then you have to multiply the 3 and the 2 to give you the 6y, 6 power to the y. All right, this one, hopefully finished off already here. Are we good there with that one? I distributed the negative 3 to the negative 2, so multiplied to give me a positive 6. That gives me a negative 3, so y still has to go down to the bottom. Final answer, x to the 6th, y to the 3. Okay, so this little rule that I used for B, technically that is something called the quotient rule, so let's cover this one real quickly here. If you have a fraction, it's called the power of quotient rules. If you have a fraction, that just means that n has to go to the numerator as well as the denominator. Also with fractions, just to make sure we didn't forget, if you have a fraction and you have a negative exponent, again, all you got to switch is numerator and denominator. That will get you the reciprocal of that. Got a couple of people writing it down, so wait a little bit. All right, let's go for it here. Just working with fractions here. So can you simplify these two real quick? Okay, 1/3 squared means that we're going to square the 1, which still keeps a 1. We're going to square the 3, gives you a 9, and we're done with A. with the -2 here, the thing I'm going to do first is I'm going to put the 7 on top, the 10 on the bottom. Don't forget I still have to square it. So squaring the 7 and then squaring the 10. How about a 49 over 100 as the final answer? Okay, so finally we get to do some fun stuff here. So now we have all the rules in front of us. Now we can start simplifying. Just a quick disclaimer, first of all. Inside your textbook, let me see if I find it. Anybody found this guy here? On page 22, towards the bottom of the page. I kind of like this here. Towards the bottom of the page, they give you a warning of sort of like what students usually do wrong, the incorrect way to do it, and then sort of like the corrected way to do it. Just common mistakes students make. So on bottom of page 22, maybe you want to sort of take a look at that just in case if you're having a little difficulty there. Okay, and then way in the bottom of page 22, it has this little thing right here. It says, what do you mean when a exponential expression is actually simplified? It's simplified when each base appears only once. So you can't have a base of 3 on top of a fraction, base of 3 on the bottom of a fraction. You're not done yet. Each exponent is a positive number, technically not a negative number, so you have positive exponents everywhere. And then you have this no concept of a power still being having to raise to a power. So no inside exponent, inside a parenthesis exponent, and outside a parenthesis exponent. None of those left. So those are 2 problems just real quickly here. All the exponent rules at our disposal. I'll let you guys try these 2 problems here. Can you simplify these all the way down? This is sort of the culmination of the exponent rules. So let's go for it here. So A, first things first, how should we solve this problem? The only thing I want to give you a disclaimer first is you could solve this by any order of the exponent rules, right? We could have taken the reciprocal first if we wanted to, and that's perfectly fine. You could have also distributed the -2 to each one of those pieces. So there is no order to exponent rules as long as you're still simplifying. So your way could have been a little different than my way. As long as you're applying the rules correctly, we'll still be okay. Whenever I see a negative, most of the time what I do, I would probably go ahead and do the reciprocal first. That's just me. So that goes away. So if I put a 1 over 2x to the 4th, now I have it to the 2nd power. Again, if you didn't do it this way, that's still okay as long as we arrive at the same answer. Okay, at this point I'm going to square this. So each one of these has to be squared. So 1 squared gives me a 1. 2 squared gives me a 4. X to the 4th squared. I know I got to multiply these guys together to give me an 8. Raise your hand if you got that one correct. Eesh. All right, about 70-75% of class. Okay, next one. First things first. Again, doesn't matter what order you're going to do this here, but I would probably get rid of this little -y to the 3rd. I want to make sure. Is this going to be a negative or a positive eventually?
Negative.
It's still going to be negative, right? Because it's 3 negatives multiplied together. So eventually we'll simplify that out. But -y times -y times a -y becomes a -y to the 3rd. Notice the 3 has to went inside the parenthesis now. I'm going to simplify it some more here. But on the bottom, I have x to the 3rd, y to the 6th. Eventually, this little negative gets to move out in front. So if you skip this step, eventually you do have to get to this step here. If you get to that step, you're doing good. Okay, still not done yet, because notice the x's repeat themselves, the y's. So I know I have a negative here. But I can start crossing things out. Everybody good there with an extra x on the bottom? And it looks like y to the 3rd, y to the 6th. I can subtract them. 3 minus 6 is -3. Or I could just say I have an extra y to the 3rd on the bottom. Question?
How did the negative go to the x from
Cool, yep. The question is, how did this negative go in front? Because this is all multiplication. Kind of like if you say 6 times -5 is the same thing as -6 times 5. The negative is sort of skipping out in front. And eventually it's just a multiplier -1. Okay, everybody good with that one? And how about -1 on top with the x, y to the 3rd in our denominator? Okay. Jumping now to scientific notation, just a quick review of scientific notation. And I'm not even going to go over the rules for it. The book assumes you know the rules because you did it so many times already here. It doesn't even talk about the rules. It just jumps into a practice problem. So can we write 732,000 scientific notation? Of course we can. So remember, for scientific notation, the number in front has to be a number between 1 and 10. What I like to do, I like to just place my decimal wherever it has to be. So if I place my decimal in between the 3 and the 2, that's still not good because that's 73.2. If I place my decimal in between the 7 and 3, that's what I want, right? Because now that number becomes a number between 1 and 10. So 7.32 is a number between 1 and 10. And now the only question is, what's the exponent have to be on the 10? Yep, we're good. So what I like to do, I like to put my decimal where it has to be and then just go to the end of the number. In this case, if I put my decimal here, I have to go 1, 2, 3, 4, 5. So this number is 10 to the 5th. Again, you'll have lots of practice on the homework, at least a little bit of practice on the homework with this stuff here. Let's see. So fun stories with scientific notation. Einstein, he stated that light controls time. So you know how if you like bounce a ball or make or an explosion happens or something, you actually can't hear it for a while. You see what happened, right? And then all of a sudden, then you hear the ball bounce, or then you hear like the rumbling of thunder, right? After the lightning, right? So sound actually takes time to get there, right? Well, Einstein was saying that in terms of relativity, light actually is part of that process. So, really weird, ready? You guys are not really seeing me, I'm not really seeing you. I see you like a split of a second later. So if you blink, that light has to travel from the blink of your eyes to me, and then I see the blink. We're good? So Einstein postulated if the sun were to explode, just because that's our source of light, we actually won't know it for about 5 minutes. And then we're like, whoa, the sun exploded. But technically, the sun actually exploded 5 minutes earlier. Is that kind of weird? Make it even more weirder. You ready? Einstein also said that if you were on a different planet and you had a telescope and you actually were looking on Earth, however many light years away, that's how you'll see our Earth. So the closest sun from us is about 4 light years away. So if you could stand on the sun, technically it's a star, and you looked at Earth, you would see what's happening on Earth 4 years ago. That's kind of cool. Isn't that weird? Recently, actually last month, there was a scientist. You guys know the formula, F is equal to M times A. I think you've seen it before. This little formula, I'm getting somewhere, just kind of making it exciting for you guys. Force is equal to mass times acceleration. That's how much force hits, so if you got hit with the 18-wheeler, you'll know how much force you got hit with, okay? So, lots of mass, lots of acceleration, and we understand this to be somewhat of a velocity quotient as well. But this is kind of weird. A scientist last month, he actually proved that this mass is actually not, how would you say, it's called not atomic mass, not what's actually not on the periodic chart, because that's what everybody thought used to be. It's not the atomic mass that's the problem. It's actually, if I can spell inertial, we're good there? Inertial mass, right? It's the mass the object is carrying with it. Cool? And then he also postulated that you can actually disturb that by electromagnetic fields. You can break up that mass. So he's experimenting on, this is kind of cool. You ready for this? Gotta pause right for the effect. Okay, so he's postulating that you can be going 100, 150, 300 miles an hour, and you can make a 90-degree right-hand turn and you won't even feel the effects thereof. If you can disturb the electronic wave in front of you, because that's the inertial mass, you're changing the inertial mass that's in front of you, and you can make right-hand turns, left-hand turns, and you won't even feel it. So that's, again, it's in sort of like a, he proved it, it's theoretically possible, and so now the game is on to see if we can actually make that happen. So it's kind of fun. Okay, enough of the fun stuff here. 20 minutes, huh? Okay. Now let's do one last problem here. So do we drink a lot of coffee in America? What do you guys say? Yes. Do we eat a lot of candy in America? Okay. So at the beginning of this section, we mentioned in 2012, Americans drank about 120 billion cups of coffee. That's a lot of calories. And then spent 28 billion on candy. That's more calories. On confectionery products. So with scientific notation, we're trying to figure out, well, how much does it cost per person? And in terms of coffee, so if we take the US population in 2012 was 114 million, and we divide these two over against each other, we find out that a person drinks about, per person in America, 350 cups per person. That's about a cup a day, isn't it? Right? Cup of Joe? Right? Except it's the people that like drink 6 cups of coffee, right? Versus the people that don't drink any at all, right? So it kind of balances out. Cup of what? Right, right. Okay, so we're going to do the cost of candy real quick here. Cost of candy evenly distributed among the population. How much do Americans spend on candy? And is this what? Is this per, yeah, it's this per year. Okay, per year. So we take this in terms of scientific notation divided by population or by person, and we find out that per year we spend $92 per person on candy, every single person, sort of thing. Okay, so your job. If the amount spent on candy consumption remains unchanged, so it's still going to be $29 billion. And the U.S. population reaches 325 million, and that's actually not true. I think we're at 330 million as of last year, end of last year. So what's the cost per person? So I'll do it with you guys here real quick here. So this is 325 million, is that right? Can you write that in terms of scientific notation? All right, I got this here, 3.25 times 10 to the 8th. We good? And then candy was already given. Candy was 29 billion, so that's going to be 2.9 times 10 to the 10. And so now the question is candy divided by population. How much candy do we consume per person? 2.9 times 10 to the 10 divided by 3.25 times 10 to the 8th. And if we do that, again, if you got a calculator, go for it. But I got 0.89 times 10 to the 2, because you got to subtract the 10 and the 8. Real quick here, though, is that a number in scientific notation? No, it's not a number in scientific. No. If this was to be a number in scientific notation, wouldn't the decimal have to be between the 8 and the 9? So technically what we should do is we put it here. So have we made the number bigger or smaller? Yeah, 0.89, now 8.9, right? So 89 cents versus $8.90, right? So since we made this number 10 times bigger, what we do is we subtract 1 from the exponent here. We good? Because we still have to have this equal sign. So make the number bigger, you make the exponent on the 10 smaller. Okay, and then That really doesn't give me a clue what's happening here. It isn't scientific notation, but what's the answer? It's 89. Yep, 89 is the answer, so therefore the final answer is, how about $89 per person for just candy? Most of it is right around October 31st. Okay, we've got 17 minutes. I do want to get to 3.0 P3 today. So let's skip out of here. Let's jump to 3.0 P3. And this one's going to go super quick, but you guys should know this already. This has to do with adding, subtracting, multiplying polynomials. So this should be pretty easy. And all the special formulas that come with it here. I think we could probably finish off this pretty quickly here. I'm going to jump through the practice problems. I think we should have a pretty good idea here. You guys have been working with polynomials for quite a while here. So polynomials. Can you add these guys up? All yours. And how many seconds do you have?
22.
22. Good. All right. Okay, so adding this up, if you want to write it as terms of addition, that's fine too. Usually we don't here, but this would be the addition look like. And then we'll understand all the way from like 7th grade, is that right? That we have to add only like terms together, so only the x to the thirds gets to be added together, gives you a 5x to the third. Only the x squareds get to be added together here, so 3 and 2 make another 5, so 5x squared. And then the first polynomial doesn't have x to it. The second just has a 2x, so we just write down the 2x as is. And then we call these guys the constant terms, the ones that don't have any variables next to them. -5 and 1 make a -4. And no erasers happening, so that's a good thing. Okay. I do have some pencils writing here, so. Okay. Notice I did skip practice problem number 1. It was more like an application question, and I think it was more confusing than actually helpful, so we'll jump from there. Okay, practice problem number 3. So this was addition. Next one should be subtraction. Can you find the difference between these two? So if you don't want to write it like this, I kind of wrote it like this. How about just write it as a subtraction problem here? Plus 7 minus a -2x to the 4th, and so on. And bless you. So all yours, 19 seconds now. All right, and I guess the quick, easy way to do it, remember that, is just to put a little plus sign here, right? And then just change very, very nicely, change all the signs of the second polynomial. We good there? You could rewrite it, but why do it? Making yourself extra work. Why do stuff like that? Okay, so once you change it to an addition problem, then we just do exactly the same thing that we did for practice problem number 2. We'll look at our is that right? Yep. So look at our x4th terms. X cubed, there's only one of them here, so that gets to be just written down. X squared, there's 2x squared here, a minus 3x squared here, so it'd be a minus x squared. No x to the 1 power here, but I have a minus x squared, a minus x over here, so that just gets to be written down. And then the constant term, 7 and 5 make 12, so how about a plus 12 at the end? Good there so far. Okay, so we got addition, subtraction. Next, what do you guys say? Multiplication. All right. Multiply -2x to the 3rd times 4x squared plus 2x minus 5. I'll just write it like this so you don't have to rewrite it again. Hopefully you guys are done, almost. So -2x to the 3rd times a 4x squared makes a -8x to the 5th. We're good there so far? Then how about a minus 4x to the 4th, and how about a plus 10x cubed? Cool. Okay, and this is called a distributive property, right? Because you're technically multiplying by a monomial times a polynomial, or one term times many terms. When we jump to the next one, I'm stalling for people to finish up. Okay, next one. Now you're looking at a binomial, 5x squared plus 2x multiplying a negative 2x squared plus x minus 7. Whew, now you got a polynomial multiplying another polynomial. In this case, what we have to do or understand is, remember, every single term here has to multiply every single term here, right? So if we're to draw, we'd have to draw this right here. The 5x squared has to multiply every single term in the other parenthesis, and then the 2x then has to multiply every single term in the other parenthesis. You guys already done here, so let me just write the answer here. Those of you catching up, go for it here. So I have a negative 10x to the 4th plus 5x cubed minus 35x squared minus 4x cubed plus 2x squared minus 14x. And then we have some like terms to be added together, is that right?
Yes.
Yeah, we've got a few here. So negative 10x to the 4th does not have anything to write together, but I have a 5x cubed, a minus 4x cubed, which gives me a plus x cubed. X squared here, so it gives me a minus 33x squared. And looks like a minus 14x, that would be the final answer. Those are all like terms being combined together. All right, and again, if I'm going a little too fast here, you can ask me to go back if you just need to finish up a little something here. The other option is you can come and talk to me right after class if you didn't get a particular slide. Third option, since I'm going to post the videos, you can always go to the video thing on there. But we're not done yet. I have 4 more problems to go. Look at that. Okay, what we usually and normally multiply is binomials. And we usually do it by the FOIL method. So using the FOIL method, can you do this? And preferably, can you do this in your mind? Can you write down straight from problem to final answer? Something about doing the inside terms and the outside terms in your mind. Cool. All right. So again, that would be a 4x squared. First term. The inside and outside term we try to do together here. So that's a 28x. Is that right? 28x minus 1x makes a positive 27x. So why do extra steps if you don't need to? And then at the end, the L of FOIL is the last terms multiplied together gives you a minus 7. Okay, good there. This one gets a little more complicated, but I think we can still handle it. So that one, first term would be 6x squared is good. All right, let's do the inside and outside terms together here. So minus 15x minus 4x would make minus 19x would be great. And then at the end, you got yourself a plus 10. Okay, so the FOIL method is the one that we use normally, multiplying 2 binomials, and then there's sometimes we have special forms with 3 more problems to go. The special form is this right here. It's called squaring a binomial sum. So instead of separating them out, remember that? We can just take the first term, we square it, and because the 2 middle terms are just going to add together, they're going to just double. We're just going to put a little 2 in front and add the 2 terms, multiply the 2 terms together. Again, don't have time to go into it. In algebra, hopefully you guys just saw how it was formed. So a plus b to the second power. Instead of doing FOIL, instead of doing a whole bunch of work, we can give the answer right away. We square the first term. We multiply the two terms together and then multiply by 2 because they double in the middle, because they're both the same when we do FOIL, and then we square the last term. Alright, how's it seen? Let me give you an example. Don't need to write it down. But if you have a 2x to the third, 2x plus 3, squared, we take the first term, we square it, we multiply the two terms together and double, and then we square the last term, and hopefully we can get right to the answer without doing that little middle section there. We good? Again, this is the example. Don't need to write it down, but you want to try this one. Ha, I switched the 3 and the 2. Alright, I'll give you the middle term here, but if you can get directly to answer, that's even better here. So take the 3x, we're going to square it, plus doubling of the first term and the last term multiplied together, and then the last term being squared. But hopefully you can go directly to a 9x squared. 6x times 2 makes it 12x. And how about a 4 at the end? Are we good there? Okay, that's one special form. The other special form is this one right here, something called the difference of squares. And I think you guys know this one as well. If you're multiplying a plus b times a minus b, if the numbers are exactly the same, the sign in the middle is changed. That means you have opposites for your outside and inside terms. Therefore, the middle terms are going to cancel each other out. So instead of using FOIL, we can just take the first term, square it, minus sign, last term, square it. So again, this is just a quicker way to do FOIL method, because as mathematicians, totally lazy people, we can figure out an easier way to do it, we'll do it. So your job, go. 1 minus 2x times 1 plus 2x. Square the first term, square the last term, put a minus in between, and done. Okay, everybody sign the sign-in sheet? Cool, okay, good. I'll pick it up soon. Okay, so how about take the 1 and square it? Technically what we can do is we can just multiply the first terms together and the last terms together, and we're done. But 1 minus 4x squared, are we good? And the last problem of them all, how about multiple variables at the same time? Here's your last problem of the day. Can you multiply this out? Alright, this is a distributive property again, right? With x squared. So x squared times y would just give me x squared y. We normally write it in alphabetical order, just to be sort of standardized. And then the x squared has to multiply to the x, gives us a x cubed. And usually with multiple variables, there really isn't any order. If you have x's and y's, you can write it like that, and that's fine.